everybody. I am talking to you today from a dark windowless cupboard in the NSQI building. Oh, my face has appeared. Hello. I'm on holiday this week, so I've recorded this little video in advance for you. Today we're going to talk about integrated single photon sources. Again, I'm just hoping to impart enough information so that you can confidently go into the teaching session with Alex and discuss the paper with him. So, the structure of today is going to be a little recap of a lot of the stuff we did last session. So, what properties we want from single photons, the difference between a deterministic and probabilistic source, a little bit about SPDC and four-wave mixing, a little bit about multiplexing, and I'll kind of just want to go into the problems that maybe we would find from the last week's paper. And finally, we'll go through this week's paper and kind of go through the main points that they're trying to convey. Okay, as I said last week, an ideal single photon source would be deterministic, so you get photons exactly when you want them on demand. They'd be bright, so you'd have as many photons as you could possibly need for your quantum photonics experiment. And also indistinguishable, so every photon that you produce is identical to the last one in terms of, temporal delay, in terms of intensity, in terms of wavelength, things like that, polarization. Okay, I'm going to go through this quite fast because we did it in the last session. And again, there's two different types of sources, broadly deterministic and probabilistic. Deterministic, for example, dots, molecules, ions, and NV centers. And they have these advantages of being, more deterministic, more on demand, but they sometimes suffer from poor indistinguishability and limited brightness when compared to the probabilistic sources. The probabilistic sources, a couple of examples of probabilistic methods of producing single photons or pairs of photons are spontaneous parametric down conversion, SPDC, and spontaneous four-wave mixing, or FWM for short. And in comparison to deterministic sources, these generally have higher brightness, better indistinguishability, but they also have the disadvantage of having probabilistic or random temporal emission of these single photons. You don't know predictably when you're going to get these photons out. And quickly, the most basic difference between SPDC and four-wave mixing is that spontaneous parametric down conversion on the left has a single input pump photon which splits into two photons, a signal and idler photon, generally of the same frequency. The difference with spontaneous four-wave mixing is that spontaneous four-wave mixing has two input pump photons, and these combine in your nonlinear medium to produce a signal and idler photon again, except that these photons will be of different frequency, different energy, but both summing to the total frequency of your two pump photons. So pause and have a look at this if that's confusing to you. There's also some really good explanations of this in Alex's notes. So that should all be a bit of a recap, and you should recognize this picture from your last lecture with me and with Alex and the paper. But I just want to kind of go over what are some problems with this study. I mean, it's an amazing piece of science. It's very much like a hero experiment. It must have been incredibly complicated and time-consuming to set up. But there's issues with it. With complexity kind of comes a lot of issues, right? Because you have to align every component. A lot of this is done in free space, which kind of opens up the experiment to being sensitive to things like temperature and vibrations and changes like that. And so that's generally why, especially in Ket Labs in Bristol, we do a lot of work with integrated photonics. So we take these experiments similar to this and we miniaturize them onto a nice stable chip to kind of get over the issues associated with a free space experiment. Okay, and that's what this paper is concentrating on. It's the integration of a four-wave mixing source onto a silicon chip. Okay, the main claims that they make in this paper are 99% spectral purity, the fact that it's silicon integrated, and silicon integrated is good because you can get nice established semiconductor foundries to make your chips for you, very high quality. They also quote 99% indistinguishability, so each photon is 99% indistinguishable from the previous one. Sorry, it's indistinguishable from the previous one 99% of the time. They quote 90% heralding efficiency and 96% visibility. Okay, and I'm going to go into each of these and what they mean and how they can make these sorts of claims. So, what did they actually do to make this integrated four-wave mixing single photon source? Well, I will explain it using this diagram, which is in the paper. They first of all pump light into this waveguide here, and there's a 50-50 beam splitter here, so you have 50% of the power running down this line and 50% of the power running down this line. You then delay one of the lines by just making the path length longer. And then the non-delayed line here, they use a mode converter to convert this first order, zeroth order mode here into this first order mode here. And so now in this waveguide here, you have two modes, first order and a zeroth order mode, kind of co-propagating through this waveguide, except this first order mode is ahead of this zeroth order mode because of this delay that we've induced here. And so the TM1 mode, so this double lobed mode here, has a lower velocity than the TM0 mode. Okay, and so this means as they both co-propagate down this waveguide and then through into this kind of spiral structure, the TM0 will gradually overtake the TM1 mode, kind of like this. And so you get a really nice overlapping of these two modes on top of each other in this spiral region. Okay, and you might be thinking to yourself, oh, we've now got the integration, interaction of two different pump lights. So you might be thinking four-wave mixing. And if you were thinking that, you would be correct. So what you have is you have the two pump photons, signal and idler, and that's exactly what happens. And this spiral basically gives enough time to ensure that you will always get a full overtake of the two pieces of pump light, maximizing the interaction time of the two of them and give you a much higher probability that you have four-wave mixing occur. So it's really nice. Okay. So you've now got a signal and an idler photon co-propagating down this output waveguide here. And all that's left to do now is to separate these two out and convert the first order mode back into a zeroth order mode, just using the inverse process of over here. And so now it looks just like a normal heralded single photon source. You have a signal and idler, and you can just do what you would normally do with a single photon source of this type. Okay, so the next bit I'm going to go through is just kind of how they've characterized the device and kind of what all these graphs mean, again, roughly. So this graph here just shows you input power versus both squeezing and pair generation rate. And you can see that as the input power is increased, you generally have more photon pairs generated, as you'd expect. You'll also notice that they have delayed versus not delayed on this graph. So this basically means the delayed is with this delay line here, and this not delayed is just having kind of two waveguides of the same length. Okay, and you can see that the delay is causing your photon pair generation rate to greatly increase. And you can also see that it's causing the squeezing rate to increase. And as I said, this delay here allows the two photons to completely overtake each other. So they have a full overlap of the entire energy field as they pass through this spiral waveguide. And so that kind of increase in interaction time between the two modes co-propagating down the spiral will give you a higher probability of generating photon pairs. But you'll also see one disadvantage, a kind of trade-off almost, is that although the input power increases the pair generation rate, you can also see that the increase of input power is causing you to go to a higher G2 heralded. And a higher G2 heralded suggests that you're getting kind of some bunching of your photons, which is not what you want from a single photon source. And so kind of what is this squeezing here? Well, this squeezing here is kind of what is happening over here. So if you're not familiar with squeezing, squeezing is just kind of altering two properties to optimize one at the expense of another. So an example of that is over here. So this is your spectral purity, joint spectral intensity for a undelayed line. So this here has no delay, okay? And you can see that the JSI is quite spread out. And basically what this spreading out of the JSI, joint spectral intensity, suggests is that you've got bad spectral purity. So you have kind of unpredictability in the relative frequencies of the signal and the idler photons. On the other hand, for this delayed line, you get kind of a squeezing in of these outer lobes into a nice symmetrical and kind of circular shape here. And this circular shape just suggests that you have a greater predictability in the relative wavelengths of the signal and idler produced, or spectral purity. And from a single photon source, this is exactly what you want. You want nice predictable photons, as always. Okay? And the nice result from the two of these is that they calculate that by introducing this delay of just 1.46 picoseconds between the signal and idler photons, which allows that nice long overlap between the two pump photons, by doing this, they increase the spectral purity from 93.1 to 99.04. And in addition to that, they also increase the photon pair generation rate. So it's kind of like a win-win. Hopefully that makes sense. So the next piece of device characterization they do is they kind of change their setup a bit. And what they have here is they have their normal single photon source or pair photon source. And then they split the signal into one line, and they run this through a 50-50 beam splitter. So in the last session, I did quite a bad job of explaining what G2 is, but I have since gone and done my homework about this. And essentially, what they have is, in a 50-50 beam splitter, if you have just single photons traveling down here, and this line here and this line here are of exactly the same length, if you look at both of these detectors at the same time, because there's only ever one photon traveling down here, you'll only ever see clicks on one of these detectors at the same time. But if you have bunching and have more than one photon simultaneously traveling down this waveguide, you can at times see simultaneous triggering of both of these detectors. And that's what they're measuring when they're measuring G2 unheralded. If you want a really good explanation of this, again, go into Alex's notes. But although with the heralded G2, you'd expect a value of 0 to indicate anti-bunching, with unheralded G2, you actually expect a value of 2 to indicate anti-bunching or single photons. And so what this graph is saying is that when you have a 0 time delay between this arm and this arm of this 50-50 beam splitter, you'll only ever see detections at one of these two SNSPDs. And this means that you're basically always producing single photons, as opposed to here, when there's a time delay between these two, where you will see kind of two photons at one time on these two detectors. So all this is saying is just another way. So they calculated they use this as another way of calculating spectral purity. So this tells you, one nice result is that this tells you you're producing nice pure single photons. And they also use this to calculate the spectral purity and verify this result here. Hopefully that makes sense. That is all explained in the paper. Okay, the next piece of characterization they do another configuration here, where they're measuring for indistinguishability. And again, indistinguishability is just how identical photons are. So if you have two photons that are exactly identical and they are completely out of phase, you would expect them to destructively interfere to a 0 intensity. And that's what this dip here is. This dip here is just indicative. If this dip dips to 0, it's indicative that the photons have destructively interfered to a magnitude of 0. Okay? And so in their characterization, when they have a 2 pi, a pi over 2 phase difference between the two source, the like the signals and the idler photons, you can see that they get very, very close to zero. So they have almost identical photons. And I haven't actually written, the indistinguishability, but I think it was very high. 99% indistinguishability they quote in this paper. So that's nice, this nice deep drop again, indicating that. Okay, so you've got nice single photons, you've got nice spectral purity, you've got indistinguishability, and the final thing they test is kind of the ability to use these photons to prepare quantum states. So they have this setup here that you can see. So they again pump light, produce single photons, and then they split these photons, they split the light here into 50-50 into two different sources. So they have two copies of the delay line and two copies of the spiral. And so you have a signal and idler up here on this top branch, and you also have a signal and idler on this bottom branch. And then they have this kind of crossover section, which basically allows signal photons only to be traveling through this top section, and idler photons only to be traveling through this bottom section. And then they use a Mach-Zehnder interferometer, which is just basically a phase changer with a 50-50 beam splitter combined. So they can basically interact two idler photons together and two signal photons together. I don't know if you remember, but from a while ago, in Krishna's half of the lecture, I talked about how inducing this phase change will, in a Mach-Zehnder interferometer, will change the output photon intensity after this 50-50 beam splitter, because you'll get destructive or constructive interference at this point and this point. So by inducing this phase change, they induce a change in amplitude of the output idler and signal photons. And they can map these intensities to kind of quantum states. So I'm not sure exactly what they use as 0, 0 and 1, 1, but I would assume that a 0, 0 state is a 0 intensity output of the signal photons here, and a 0 intensity output of the idler photons here. Okay, and they would do that by creating a phase change that made the two signal photons pi over 2 out of phase, so that they perfectly destructively interfere. Okay, and that's what this is. So pi over 2 phase change, destructive interference, you get 0 clicks at your output SNSPDs. And so what they do, they measure fidelity, and a fidelity is just a measure of kind of, in basic terms, it's a measure of what you expect versus how often you actually get what you expect. Okay. And so this graph here, they've got 4 bars, and you can see these dotted lines. So if you had 100% fidelity, okay, and so what you like are trying, the phase that you're trying to, the state that you're trying to create, like a 1, 1 or a 0, 0 state, if it was always exactly what you wanted, you'd expect all of these red bars to go up to these dotted lines here, okay? And what you can see is that these red bars here, which are the actual measured fidelities, they come very close to being ideal fidelity here. I don't remember if I went through all of these states, but 0, 0 is probably a 0 intensity of both of these outputs. A 1, 1 is probably like a 100% like amplitude output of these single photons, and 1, 0 is probably like this one having output and this one having no output, and 0, 1 is probably the opposite, so this one having output and this one not having output. Okay, and so this graph here basically just says if they try and create a 1, 1 state, they will almost always, 98.9% sure that they will get that state. Okay, I'm sure Alex can explain this much better than I can, but that's as good as I can do, unfortunately. Okay, and the final thing they measure along with this graph is just the joint spectral intensity of the two sources individually. And I think the point of having these graphs here is just to show you that both sources are almost identical. And that's basically the whole paper. Hopefully that should give you enough information to kind of confidently go and talk to Alex about this and come in with some nice intelligent questions to him. Sorry I couldn't be there in person, but it's good for me because you can't ask me any more questions that I don't know the answer to. So yeah, just to summarize, free space optics and experiments like we saw last week are really cool, really impressive that people can set these up, and they're really good for showing us that these things are possible. However, there are advantages such as temperature and vibrational stability of having integrated photonics. And the integration of this into a silicon platform is particularly beneficial because silicon is extremely pure. You get low loss of light through silicon at 1550 nanometers. And we can basically pay foundries to manufacture us really high quality chips with low losses. It works on this kind of delay line approach. So you've got two different modes which travel at two different speeds, which overlap and overtake each other in this spiral region, produce two single photons, and these single photons have very favorable properties. These favorable properties are really good spectral purity, good pair generation rate, good anti-bunching performance, good indistinguishability, and finally, if you want to use this as a method for preparing quantum states, you get really good 98.9% fidelity. Okay, thank you for listening. I'm going to leave and go on my holiday.